Hello and welcome to today's debate, low temperature solders, and what are the challenges and why do we need them? Do low temperature solders increase reliability or do they increase the potential for CTE mismatches? What are the applications and what are the trade-offs? I've got a really eminent panel to discuss this today. To my extreme right we have Chris Nash from Indium Corporation.
Hi, Trevor.
Hi. To his left we have Keith Swetman from Nihon Superior.
Hello there.
To his left, we have Tim O'Neill from AIM Corporation.
Hi, Trevor.
Yep. And then to my right, we have Watson Seng from Shenmao. So,
Hi, Trevor.
Hi. Welcome, gentlemen, and thank you for joining us this morning. I'm going to jump in with my first question, which is what are the principal applications for low-temperature solders? Let's push that out with Chris.
Sure. I think a lot of the applications for low-temperature solder are really focused on the computing and handheld mobile devices. Those are the guys that we see that are coming to us the most often for low temp. And I think it's really due to the warpage issue. The processors that the mobile guys, the computing guys are using are getting thinner. A lot of them are cordless processors, and they tend to warp more than a lot of other processors in the past.
Right.
So I think the biggest challenge there is the processing. However, there's traditional applications as well, like secondary processes in shield attach, for instance, that people are still interested in, or just your everyday step soldering applications where they would use a higher temp, say SAC alloy, than a secondary process of a low temp alloy.
Right, and I'm guessing the packaging size is so small that there's not the space for putting heat sinks or anything like that around them either. So you need a new approach.
Correct. Yep.
Right. Anybody got anything different to add to that? Any other applications that you see for these types of low temperature solders?
Well, these low temperature solders have been around for a long time. So what is different now is that they're being used in places where they weren't previously used. Chris mentioned some traditional applications and some new ones, but at the moment it's split between two categories. Those who want to minimise warpage of IC packages and those who want a lower temperature process to save energy and make possible the use of cheaper materials. It's almost really two different categories of low temperature application in this generation.
So energy saving is a big component because presumably you're running your ovens at a lower rate. You're not having to invest as much in energy there, so there's an energy saving component to that. Presumably that would be emphasized in countries where you've got high electricity costs and things like that as well. Are you coming across anything like that, Tim?
Not the energy savings per se. These guys have touched on what I think are the key reasons that people are investigating low temperature alloys. Component warpage, reduced energy costs, cost savings, as many of these don't contain silver or a low percentage of silver.
Okay.
There's a materials cost savings as well.
Mm-hmm.
But a few things had to happen in order for us to arrive at this juncture, and that's basically RoHS 2 eliminating lead from the supply chain completely, because prior to that, bismuth alloys were sidelined because the presence of lead could lead to the formation of a ternary alloy with a 97 degrees C melting temperature.
Right.
So now that the supply chain is largely scrubbed, these are getting revisited by a variety of industries and looking to see if there are applications that they can enjoy benefits. Looking at our current user base for these low temperature alloys, Chris mentioned a couple of them, step soldering, but also low-cost disposable applications that are temperature sensitive because they're using inexpensive materials, disposable medical devices and things along those lines. Mm-hmm. The turkey timer in a butterball turkey, when the thing would pop, that was a little bismuth alloy that was in there. So
right.
They were very specific temperature requirements that the customer was trying to achieve.
Right, yeah. No, Watson, Tim makes a very good point there that RoHS 2 opened up the market to be able to use bismuth-based materials. And I think a lot of you are using bismuth solutions for your low-temperature alloys. Would you agree?
Yes, it gives us more freedom to select the different elements to be added in the low temperature alloys. Yeah, we tried many different combinations, and some of them shows good reliability and keeps the low melting temperature as well.
Right. Okay. So, I mean, if you're reflowing your boards at lower temperatures, is that also increasing the reliability?
I think bismuth contained alloys are relatively brittle. Bismuth by nature is going to fracture on a plane. So using a bismuth alloy is going to potentially decrease your reliability in certain applications from drop shock performance or thermal cycling performance standpoint.
Right.
So Indium Corporation is looking at a new alloy technology with Durafuse LT. It's a high reliability, low temp offering from Indium that employs a low melting point powder mixed with a SAC 305 powder in solder paste form. And the drop shock performance is actually improved with regard to the alloy, and thermal cycling has been improved as well compared to bismuth.
Right. So you're using an alternative to bismuth, which is a proprietary alloy
That's correct.
You've developed. Okay. Yeah. Is there a way of mitigating the brittleness of the bismuth in these low temperature applications?
Yes, well, what Chris is talking about is a different process, which I think you describe as liquid phase diffusion bonding, where you're mixing a high temperature and low temperature solder and letting them react. But the reliability, I think the interesting point is that the industry seems willing to accept a lower level of reliability than is achievable with other alloys. And this suits applications where, at the moment, you may be getting more reliability than you need. I mean, I'm thinking of a TV remote, which really doesn't have to put up with very much. You can make it a lot cheaper.
With a lot of shock. I mean, these things get thrown around.
Allowing for that. So you can tolerate a lower level of reliability than you would in a military aerospace circuit board. So that's one factor. But you can also increase the reliability by reducing the amount of bismuth to the point where it's not the main matrix of the microstructure. You've got to go to a higher melting point, but you avoid this problem that Chris mentioned, that bismuth is very brittle. So if you can make the structure predominantly tin and sacrifice a little bit of melting point, you can increase reliability.
Okay. So, I mean, Tim, if tin bismuth was not an acceptable solution back in the 90s when we were looking for a lead-free solution, why is it acceptable now?
Well, as I mentioned, the elimination of lead predominantly has what has people revisiting it. I also think the climate for looking at alloys that have application-specific properties has become more commonplace. I'm assuming when we all got in the business, we all were selling 6337, 95% of our business.
Yeah.
And then as soon as lead-free came along, SAC 305 became the de facto standard. And then immediately, cost-sensitive applications were looking for alternatives. So alternative alloys came out to eliminate the silver, lower the cost. And that has changed the mindset of the user base so that they're much more willing to experiment with alloys that have a particular characteristic that satisfy the need of the application. So I think you're going to see further diversification and fragmentation of the alloy market, where they will be making alloy selections based on very specific criteria. I think one general statement, and I want to emphasize a point that Keith made, was that none of these alloys, to the best of my knowledge, have similar reliability characteristics of SAC 305, and I'll just use SAC 305 as the benchmark. So you are accepting some degree of loss of reliability. The question is that acceptable for the application, whether it's a TV remote? I assume it will be consumer electronics that live in happy places.
Right.
That will be the first things to go, and then once the confidence level rises, people will start to experiment with more challenging applications and environments. I don't think a leopard will change its spots, however. High bismuth alloys are going to behave like high bismuth alloys regardless of what pixie dust gets put in there to try and improve the characteristics. The
Right.
gains will be incremental, not revolutionary.
Right. Okay.
My opinion is compared to the 90s, right now the electronic products becomes more complex. So in some
And
products,
smaller.
yeah, smaller, and in some applications you need a first reflow, second reflow, even the third reflow. And if we take sexual fire as a baseline in medium melting temperature, we need a higher melting temperature and lower melting temperature so that when we run the multiple reflows, the earlier solder joint will not remelt again. So that is why the industry is more would like to have more choices on different melting temperature areas.
Yeah, I would think, people who are making consumer products are not going to be very keen on doing 2 and 3 different temperature reflow runs. I would have thought, but I don't know. Some of these people are using the tin bismuth solder balls for BGA applications. I mean, how do you maintain consistency and reliability in these applications?
I think predominantly the industry is using SAC, some form of SAC for their solder balls on BGA components. So the interface of the solder joint would actually be at the SAC interface with the ball. So the ball is not actually going to fully homogenize with the bismuth tin solder alloy or any of the low temp alloys that are being used. So I think the real play is how much can we diffuse the SAC alloy into the bismuth tin silver solder or the low temp solder to gain a little bit more tin in that interface.
Okay. Would you agree with that, Keith? Is that
Oh yes, well that's the reason that this what is coming to be known as hybrid reflow. This is how it works. You start off with a low melting point tin bismuth solder that has pretty awful properties. But as it gets diluted, or as the tin content increases, as the solder ball dissolves in it, it becomes a lower bismuth alloy and a stronger alloy. So in fact, this process of hybrid reflow depends on that dilution effect that Chris mentioned, to make it a higher tin alloy than it was at the beginning.
right? Okay. So, Tim, if you're introducing some of these elaborate low temperature processes into the board, how do you maintain the reliability, and what are the trade-offs with the other devices that are on that board?
Interesting question. The reliability characteristics of the pure tin bismuth alloys, I say pure tin, the with only the two-part alloy with some, the two-part alloy with some sort of alloying dopant or element is going to have characteristics that are less reliable than SAC. So again, using SAC as the benchmark, I think you're just going to have to match the application and the materials with the expected reliability. There's no, I don't see another way around that, and it's going to require a thorough understanding of the end user and the material set that they have available to them.
Right. Okay. So, Watson, I'll pass the next question to you, which is what work has been done to ensure the compatibility of these low temperature solders with, other board finishes, coatings, and that type of thing.
We have done a lot of tests with low temp solder on different board surface finishes, like OSP, nickel gold, immersion tin, and immersion silver.
Yep.
And all of these shows good compatibility with low temp solder pairs. However, we do see some compatibility between the coatings of the connectors. Yeah, if it's a nickel coated connectors, the process needs to be improved so that the IMC can grow with a certain thickness and to ensure the solder joint reliabilities.
Right.
They I think the low temp realm is similar to SAC-305 with conformal coating compatibilities, overmold compatibilities. You still have no clean flux residue left on the board, and that's very, very similar to what we're seeing with SAC-305. So I don't see that to be too much of a concern, and a lot of these alloys are tin-based alloys, so tin-based is going to wet very well to any of the metallizations that are currently being used in the industry. So I would agree with Watson there.
Yeah. Okay. Anybody else got anything to add to that topic?
Well, I would just say that we still have the same problems and concerns that we have with SAC-305. My customers are still worried about voiding. My customers are still worried about solder bowling. They're still worried about SIR values and all of the things that go along with SAC-305 soldering. So those don't get set
Solved.
aside because you've gone to a tin bismuth alloy. All you're doing is adding another level of complexity to determining the reliability profile of the solder joint that you're making.
Yeah, I would agree, but there's trade-offs on both sides. There's a little bit less in reliability, but there's energy savings, there's cost savings, as you said earlier. It depends what you're building. But do you think it's going to be a phenomenon that is going to expand beyond the small applications that we've got at the moment? Do you think as we start to understand it better, the applications are going to expand?
I think you're right, that as confidence in the low temperature processing technology increases, I think people will start to realise that maybe they don't have to be using SAC in everything they make, and they'll start to differentiate the market, particularly in the cost-sensitive end. And I think there's going to be an increasing use of them till they'll probably become a significant part of the overall market. Because a huge amount of electronics is in that category where high cost is critical and reliability is a secondary consideration. So I think it's the beginning of new era.
A lot of your consumer electronics are quite disposable these days. So I agree. Anyway, gentlemen, I want to thank you for joining the debate this morning. It's a great topic, and I think it's one that we're going to be talking about for a while to come. So I want to thank Chris Nash from Indium Corporation, Keith Swetman from Nihon Superior, Tim O'Neill from AIM, and of course Watson Senning from Shenmao. And thank you for joining us today.